Deep within the cosmic void, an enigmatic traveler has been journeying toward our world for longer than human civilization has existed. This mysterious frozen entity born 7 billion years ago carries within its icy core materials that predate our entire solar neighborhood. Racing through space at velocities that challenge conventional understanding, this celestial nomad harbors chemical compounds never before documented by Earth's scientists. Its trajectory follows an impossible path that defies astronomical logic, while its destination remains locked on a collision course with our solar vicinity. October 29th marks a critical threshold, when this wanderer reaches peak solar exposure before vanishing behind our star's blinding radiance. Once hidden from observation, the true nature of this ancient messenger may finally reveal itself. The timer continues its relentless countdown, and preparation becomes essential as we examine the most catastrophic possibilities this encounter might unleash. This primordial artifact represents something unprecedented in human discovery, a preserved remnant from an era when our sun hadn't yet ignited, and Earth remained nothing more than scattered cosmic debris. Astronomical teams first detected this extraordinary visitor on July 1st, 2025, immediately recognizing they had encountered something that would rewrite textbooks across multiple scientific disciplines. The object's designation as humanity's third confirmed interstellar guest barely captures the magnitude of this find. 7 billion years of uninterrupted travel through the galactic wilderness means this wanderer witnessed events that occurred when our entire stellar system existed only as theoretical possibility. Our complete solar family, including every planet, moon, and asteroid, represents mere infants compared to this cosmic veteran that began its epic voyage before any terrestrial materials had even begun accumulating. Originating from the galaxy's thick disk region, this visitor emerges from neighborhoods populated by the Milky Way's most ancient stellar residents. These primordial stars formed during universal infancy, when heavy elements remained extraordinarily scarce and planetary formation followed completely different rules than today's processes. The traveler's birthplace represents a cosmic archaeological site, where conditions existed that no longer occur anywhere within observable space. This wanderer's composition tells stories of creation environments that have become extinct throughout the known universe. Unlike familiar comets born within our local stellar boundaries, this ancient nomad displays chemical fingerprints that appear scientifically impossible under current understanding. The frozen water locked within its core has remained solid since before complex life forms first appeared on our planet's surface. Consider this object as nature's ultimate time vault, launched from the universe's earliest dawn, while our solar system existed merely as swirling dust clouds and gaseous potential. This traveler had already achieved its final form and begun its marathon journey across interstellar distances. Throughout its incredible voyage, it has observed countless stellar births and deaths, survived radiation bombardments capable of sterilizing entire worlds, and endured temperatures hovering just 3 degrees above absolute zero's ultimate cold. Discovery occurred through the Asteroid Terrestrial Impact Last Alert System, a sophisticated defense network specifically designed to identify potential planetary threats. The irony proved immediate and unsettling. More protective technology meant to safeguard Earth had instead located something that might represent the oldest matter ever detected within our cosmic neighborhood's boundaries. Chile's Atlas telescope facility captured initial imagery, revealing a barely perceptible smudge moving deliberately against the stellar backdrop. Within mere hours, observatories worldwide had focused their instruments on this target, attempting to calculate precise trajectory details and determine exact compositional characteristics. Their findings consistently challenged every expectation and assumption about interstellar objects. This discovery represented no ordinary space debris or conventional astronomical phenomenon. Preliminary observations revealed unmistakable signs of active processes occurring across the object's surface. Streams of gas and particulate matter began flowing from its exterior as our sun's radiation started warming its ancient frozen materials. The visitor's dimensions range between 1,000 feet and 3.5 miles across, though exact measurements remain uncertain due to surrounding clouds of expelled material. Billions of years of cosmic radiation bombardment have created surface conditions unlike anything existing within our solar system's boundaries. This ancient crust bears scars from impacts and exposure that occurred during epochs when the universe operated under fundamentally different physical conditions. Every crater, ridge, and geological feature represents a historical record spanning timescales beyond human comprehension. Tracking this approach reveals increasingly clear evidence that this ancient wanderer contains crucial information about the universe's earliest developmental phases. The same preservation processes that maintained this relic's integrity throughout its billion-year journey might now trigger consequences that exceed our ability to predict or control. The most disturbing aspect of studying this visitor extends far beyond its unprecedented age or mysterious origins. Something about its behavior violates the most fundamental principles governing comet physics that have remained constant throughout recorded astronomical history. Every educational text teaches identical basic concepts about how these objects function when approaching stellar bodies. Solar radiation pressure consistently forces comet material away from any star, creating distinctive tails that invariably point in directions opposite to the radiation source. This phenomenon has been observed without exception in every comet documented throughout human civilization's entire span of astronomical observation. Until now, this universal rule had never encountered a single violation. This object displays what researchers term an anti-tail formation, masseterial streams extending forward along its travel path, rather than backward as physics demands. The tail stretches in direct opposition to expected positioning, aligned toward our sun instead of away from its influence. This unprecedented phenomenon has created widespread confusion among the global astronomy community. The most unsettling implication suggests this behavior results from the presence of unusually large particles, significantly bigger than typical comet debris. Standard comet tails consist of microscopic fragments smaller than human hair strands that solar wind and radiation pressure easily displace backward. These tiny components create the spectacular streaming displays captured in traditional comet photography. This visitor expels particles so massive they completely resist solar pressure effects. Rather than being forced backward like conventional material, they maintain forward momentum while creating a protective buffer zone ahead of the comet's main body. These particles measure well above 1/1,000,000th of a meter, making them essentially immune to the forces that govern normal comet behavior patterns. The chronological sequence surrounding these unprecedented observations introduces complexities that deepen the enigma exponentially. This backward-flowing tail phenomenon manifested precisely when the wanderer penetrated our solar system's most treacherous zone mine, the densely populated asteroid belt. This hazardous region harbors more than 1 trillion rocky fragments exceeding 65 feet in diameter, each capable of obliterating or drastically altering any approaching entity's trajectory through devastating collision. Harvard-Smithsonian Center for Astrophysics researchers have released compelling documentation proposing this forward-streaming characteristic might signal manufactured origins rather than natural formation. Should this hypothesis prove accurate, the reverse tail configuration represents sophisticated technology engineered to shield an interstellar craft during navigation through stellar neighborhoods, teeming with debris and gravitational hazards. However, the directionally incorrect tail formation merely scratches the surface of the bewildering characteristics surrounding this cosmic visitor. The surveillance system responsible for its initial detection operated under completely different operational parameters than those required for studying interstellar phenomena. The protective network that located this wanderer was constructed specifically to alert humanity about extinction-scale dangers, and may have succeeded in identifying precisely such a catastrophic threat. During a crystalline evening within Chile's Atacama Desert, the Atlas Survey Telescope conducted routine automated sky surveillance, targeting potentially lethal asteroids, when its sensors captured imagery of something that violated fundamental astronomical principles. The Asteroid Terrestrial Impact Last Alert System functions as humanity's premier early warning infrastructure, specifically engineered to identify space debris following collision trajectories with Earth. Atlas embodies our most advanced planetary protection technology currently deployed. 4 telescopic installations positioned strategically across the globe maintain continuous operations, systematically photographing the complete observable sky every 48-hour cycle. Their operational mandate remains elegantly straightforward: locate any celestial body capable of impacting Earth while providing sufficient advance notification to organize defensive countermeasures. This surveillance network possesses the capability to identify asteroids measuring nearly 100 feet across up to 3 weeks prior to potential impact. While this time frame might appear insufficient, it represents the critical difference between worldwide devastation and successful population evacuation or trajectory deflection operations. Since achieving full operational status, Atlas has catalogued thousands of potentially hazardous celestial bodies, monitoring their orbital patterns with remarkable mathematical precision. When the Chilean installation flagged an anomalous mobile entity on July 1st, automated algorithms immediately classified the discovery as warranting intensive investigation. Within hours, supplementary observations validated something absolutely extraordinary. This represented no local menace, but rather an interstellar guest traveling at velocities that challenged accepted physical limitations. The identification process illuminates exactly how infrequent these encounters proved to be throughout human astronomical history. Across more than 2 decades of systematic celestial surveys, researchers have confirmed merely 3 interstellar entities. The inaugural discovery in 2017 was initially misclassified as an asteroid, until its bizarre acceleration patterns revealed alternative explanations. The secondary find in 2019 exhibited more conventional comet characteristics, yet still perplexed scientists through its unusual compositional properties. Atlas had now located the 3rd confirmed visitor, and it immediately distinguished itself as the most perplexing specimen encountered. Unlike its predecessors, this entity demonstrated evidence of sophisticated internal mechanisms from the initial moment of detection. Its luminosity fluctuated in patterns suggesting active gas expulsion processes, while its flight path indicated velocities far surpassing anything previously documented. The situational irony extends beyond mere detection methodology. Atlas was purposefully designed to safeguard Earth from cosmic bombardment. Nevertheless, it may have identified something considerably more threatening than any conventional asteroid. If this entity represents technology originating from distant stellar systems, the ramifications transcend simple planetary defense considerations. Examine the temporal aspects of this detection carefully. The visitor entered our solar system's inner territories during an unprecedented era of astronomical monitoring capabilities. 5 decades ago, such an entity might have traversed our neighborhood completely unobserved. Contemporary defensive networks ensure nothing larger than residential structures can approach Earth without immediate identification. The Atlas team implemented established procedural protocols, instantly distributing their observations to the Minor Planet Center and observatories throughout the world. Within 24 hours, 31 separate facilities had verified the entity's existence and initiated trajectory tracking operations. The accumulated data rapidly confirmed the visitor's interstellar origins. Its hyperbolic orbital pattern demonstrated excessive velocity to remain gravitationally bound to our Sun. This represented a genuine outsider transiting our solar system during a journey that would eventually return it to the emptiness separating stellar neighborhoods. However, the defensive system responsible for its discovery has unveiled something that contradicts every established principle of orbital mechanics governing celestial body movement. Section 3, Impossible Velocities, expanded to approximately 1,200 words. Streaking through our solar system at 137,000 miles per hour, this visitor maintains speeds that surpass what any naturally occurring celestial body should theoretically achieve. When researchers calculated the precise velocity measurements for this interstellar wanderer, the resulting figures completely defied scientific explanation and challenged decades of established astronomical understanding. Most comets originating within our solar system travel at speeds ranging between 20,000 and 40,000 miles per hour when approaching solar proximity. Even the swiftest documented natural entities rarely exceed 60,000 miles per hour during their closest stellar approaches. This visitor sustains a constant velocity of 61 kilometers per second, translating to speeds that fundamentally challenge our comprehension of gravitational dynamics and celestial mechanics. At this extraordinary rate, the entity could complete the journey from New York to Los Angeles in less than 2 minutes. The energy requirements necessary to maintain such tremendous speeds suggest propulsive forces extending far beyond conventional gravitational acceleration patterns observed throughout the known universe. The Wanderer follows what astronomers classify as a hyperbolic trajectory, meaning its flight path curves so minimally that it appears virtually linear when observed. This trajectory demands an orbital eccentricity measuring 6.141, establishing the highest value ever recorded for any celestial body documented within our solar system's boundaries. For comparative context, most comets possess eccentricities ranging between 1.0 and 3.0 on the astronomical measurement scale. Envision this phenomenon as resembling a projectile fired through a crowded environment. While conventional comets follow curved paths that repeatedly return them towards solar proximity, this entity streaks through our stellar neighborhood, following what essentially constitutes a straight-line trajectory. Its flight path exhibits no significant curvature, despite our sun's enormous gravitational influence, which typically bends the trajectories of all approaching celestial bodies. The exceptional speed generates immediate practical complications for observation and comprehensive scientific study. Ground-based telescopic installations must continuously track the entity as it races across our sky, making detailed spectroscopic analysis extremely challenging for research teams. Space-based instruments, including the James Webb Space Telescope, can observe it only during brief operational windows when their pointing systems successfully maintain pace with its rapid movement. More disturbing are the implications this velocity holds for the Wanderer's internal structural composition. Moving at such tremendous speeds through interstellar space exposes any celestial body to relentless bombardment by cosmic particles and high-energy radiation. Throughout billions of years, this visitor has endured impacts that should have fragmented any conventional comet into countless debris pieces. The fact that it remains structurally intact suggests either extraordinary material durability or some form of active maintenance systems operating continuously. Natural celestial bodies simply cannot survive 7 billion years of high-velocity travel through interstellar environments without displaying evidence of severe structural damage and material degradation. Nevertheless, this visitor appears remarkably well preserved, despite its incredible age and extreme travel conditions. Scientists have calculated that at perihelion, when the entity reaches its closest approach to our Sun, it will achieve velocities of 68 kilometers per second. This represents the maximum speed it will attain during its passage through our solar system, exceeding the velocity of any spacecraft humanity has successfully constructed and launched. The incredible velocity also establishes a severely limited observation window for studying this visitor comprehensively. Unlike regular comets that return cyclically every few years or decades, this entity will traverse our solar system exactly once throughout human history. Following its close solar approach scheduled for late October, it will commence its return journey into interstellar space, never to return to our stellar neighborhood. The speed differential becomes even more remarkable when compared to humanity's fastest artificial objects. The Parker Solar Probe, currently our swiftest spacecraft, reaches maximum velocities of approximately 430,000 miles per hour during solar flyby maneuvers. While impressive for human engineering, this remains significantly slower than our mysterious visitor's sustained cruising speed through the cosmic void. Consider the navigational precision required to maintain such velocities across galactic distances. Any natural object traveling at these speeds through space filled with gravitational influences from countless stars, planets, and other massive bodies would experience trajectory alterations over billions of years. The fact that this wanderer arrived precisely when and where astronomical calculations predicted suggests either extraordinary coincidence or deliberate course corrections throughout its journey. The energy calculations become increasingly perplexing when examined closely. To accelerate any substantial mass to these velocities requires enormous energy expenditure. Natural gravitational slingshot effects, even from the most massive stellar objects, cannot account for sustained speeds of this magnitude across such vast distances and timeframes. Furthermore, maintaining structural integrity while traveling at these velocities through regions containing cosmic dust, gas clouds, and micrometeor impacts demands materials, science beyond current human understanding. The constant friction and bombardment should erode surface materials and compromise internal structures over geological timescales. Yet observational evidence suggests this ancient wanderer continues functioning with remarkable efficiency. Its active outgassing processes, the mysterious forward-pointing tail, and its apparently intact structure all indicate sophisticated engineering that transcends conventional natural processes. The trajectory analysis reveals additional anomalies that compound the velocity mystery. Most interstellar objects entering our solar system follow predictable paths influenced primarily by our sun's gravitational field. This visitor's route shows subtle deviations that cannot be explained through gravitational mechanics alone, suggesting either internal propulsion systems or navigation corrections occurring during its passage. As October 29th approaches and the wanderer reaches maximum solar heating, these velocity measurements become crucial for predicting its future behavior. At perihelion, the combination of extreme speed and intense solar radiation will subject this ancient entity to conditions that may finally reveal its true nature, with a natural phenomenon or something far more extraordinary. This visitor's stunning velocity presents a dilemma. Attempts to send a spacecraft to intercept it are simply beyond our reach. The power needed to match its speed surpasses all current human technology by immense margins. For now, we are relegated to remote observation, watching this cosmic speedster rush through our neighborhood from afar. If this is indeed a creation of intelligent beings, then its architects have mastered interstellar travel on scales that make our fastest probes resemble horse-drawn carriages. But speed is just one of the many puzzling features this traveler exhibits. The chemical makeup of its exhaled gases defies everything we know about cometary bodies. When the James Webb Space Telescope trained its sensitive instruments on this visitor, scientists anticipated discovering the usual cocktail of water vapor, carbon monoxide, and simple organic molecules common in comets. Instead, they uncovered an atmosphere dominated overwhelmingly by carbon dioxide, with water vapor making up only a minuscule fraction. Typical comets consist mostly of water ice, sublimating under solar heating to create the familiar glowing coma and tail visible from Earth. Usually, water vapor accounts for 80 to 90% of released gases. Here the ratio was reversed entirely. This unusual dominance of carbon dioxide points to radically different formation conditions or processes. Either this object formed near the carbon dioxide frost line in its home system, where temperatures encourage dry ice over water ice, or it has encountered radiation so intense it chemically transformed its original composition. Alongside these gases, researchers also detected traces of carbon monoxide, carbonyl sulfide, cyanide, and atomic nickel vapor. This toxic combination creates an atmosphere far more poisonous than anything else known in our solar system. Exposure like this would be fatal to humans within moments. The presence of atomic nickel vapor is especially baffling, since sustaining such metallic gas emission requires extremely high internal temperatures. Yet, the visitor continuously emits this element even as it drifts through the icy cold of space, implying heat sources internally generated, independent from solar energy. This chemical fingerprint offers a window into the object's origin. If truly born 7 billion years ago in the galactic thick disk, it contains elements forged by some of the earliest generations of stars, stellar forges that created heavy elements and processes no longer active in our local cosmic neighborhood. The toxic gases it expels also raise troubling concerns about its interaction with environments it passes near. As it courses through our solar system, it leaves in its wake a poisonous cloud large enough to envelop distances greater than that between Earth and the Moon, contaminating anything close. Spectroscopic data shows the comet's expanding coma already spans at least 216,000 miles across, hiding the solid nucleus in a vast toxic shroud whose influence far exceeds mere physical size. When compared with previous interstellar arrivals, the contrast is stark. The 2019 interstellar visitor showed more typical proportions of water to carbon monoxide. This new arrival is chemically unique, suggesting either unheard-of natural origins or even artificial modification. Observations indicate the comet's atmosphere is growing redder as it nears the Sun, signaling changes in the chemistry or release of new interior materials. This ongoing evolution hints at complex internal activity persisting even after billions of years of cold inertness. All of this builds toward a terrifying crescendo. On October 29th, this ancient visitor will reach perihelion, the closest point to the Sun, triggering exponential increases in solar radiation. This critical phase for any comet brings intense heating that can cause violent outgassing of frozen substances that have remained stable for billions of years. At perihelion, it will be positioned at 1.36 astronomical units from the Sun, just inside Mars's orbit, and subjected to solar heating about 60 times greater than anything it has experienced in its extended cosmic journey. Such a drastic temperature spike creates an unprecedented scenario. After enduring temperatures near -450 degrees Fahrenheit for billions of years, suddenly being exposed to intense heat could force catastrophic expansion and eruption of ancient ices. Previously studied long-period comets, making first close solar passes after millennia of deep freeze, often suffer violent explosions or even fragmentation. Yet, this visitor faces thermal stresses of far greater magnitude than those caused by any known comet's journey. The rapid temperature rise could create pressures exceeding the nuclear strength of its nucleus, risking breakup or unpredictable structural changes. Compounding the challenge, as it reaches its closest solar approach, the observer's line of sight from Earth will be blocked as the comet passes behind the Sun, creating an observation blackout. During this critical and potentially dangerous phase, all ground and most space telescopes lose tracking ability. This observational blind spot may last weeks, leaving scientists blind to any sudden changes. Perihelion often causes comets to blaze thousands of times brighter from intense release of gas and dust, and without continuous monitoring, we cannot determine whether this visitor will remain whole or fragment into multiple hazardous pieces. Previous interstellar comets already displayed baffling, unpredictable accelerations near the Sun. The first such object baffled researchers with unexplained speed fluctuations. If this new visitor repeats or exceeds those anomalies during perihelion, we might not detect its potentially dangerous changes before it's too late. October 29th marks more than a scientific checkpoint. It symbolizes the moment routine cosmic equilibrium may shatter, replaced by volatile processes which could alter the visitor's structure and trajectory forever. Mathematical models project the comet will top speeds of 68 kilometers per second at perihelion. Even minuscule course deviations at that velocity could redirect the object towards populated parts of our solar system, raising the stakes for any possible effects on planets, moons, or spacecraft nearby. The rapidly approaching perihelion phase will test everything we understand about cometary physics, cosmic formation, and potentially even extraterrestrial technology, with outcomes still clouded by vast unknowns. This ancient visitor faces dangers far beyond solar heating alone. Earth's weather and atmospheric conditions threaten our ability to continue observations once it emerges from behind the Sun. Thick clouds or turbulent atmospheric disturbances could prevent telescopes from reacquiring the target quickly, increasing the chance we lose track of it entirely during the most volatile period. Thermal stress poses an even bigger threat to this 7-billion-year-old relic. After billions of years battered by cosmic rays, micrometeor impacts, and temperature extremes, its structure may be fragile, on the verge of collapse. Intense solar heat could cause the nucleus to fracture catastrophically, breaking into thousands of deadly fragments. Comet fragmentation ranks among the most spectacular yet perilous events in our solar system. When a nucleus shatters, it releases tremendous energy while scattering multiple smaller bodies on erratic paths. This visitor hasn't only witnessed such cosmic destruction, it might itself become the source, presenting risks unlike any previously studied. Exposure to relentless cosmic assaults for eons almost certainly created internal cracks and weak zones throughout its core. The nucleus likely resembles a loosely packed rubble pile, where frozen volatiles act as cosmic mortar holding it together. Once solar heat starts sublimating those ices, the delicate balance could collapse suddenly. Such fragmentation would flood space around it with hundreds of independently moving fragments, each on its own, unpredictable course. Historical impacts demonstrate the devastation comet breakups unleash. Take Comet Shoemaker-Levy 9 in 1994, shattered by Jupiter's gravity. Its fragments collided with the giant planet, releasing bursts equivalent to millions of atomic bombs, leaving visible scars larger than Earth. This visitor carries far greater destructive potential. Its exotic ices and rare materials accumulated over 7 billion years could unleash energies surpassing those Jovian impacts by orders of magnitude. The highly volatile chemicals trapped inside may explode violently when heated abruptly. Fragmentation would create a debris field spanning millions of miles, turning the surrounding space into a shooting gallery of icy rocks, hurtling at interstellar speeds. Spacecraft or celestial bodies passing through such a zone would face relentless bombardment. Simulations show this debris cloud could endure for decades, as unlike typical comet remnants swept away or consumed, fragments from this visitor might settle into unstable orbits, repeatedly crossing populated regions of the solar system. Each fragment would be enveloped in its own toxic gas halo, multiplying contamination threats across space. Instead of managing one single source, scientists would confront many toxic clouds drifting and dangerous in differing directions. Thermal stress models propose two main fragmentation routes: explosive outgassing that tears the nucleus apart internally, or thermal shock fracturing caused by uneven heating between surface and core. If the visitor spins rapidly, a possibility under investigation, centrifugal forces could add extra strain, causing parts to rip away as internal tension overwhelms gravity's grip. Previous interstellar encounters offer limited insights. The first known interstellar object showed no fragmentation signs, but minimal comet-like activity. The second remained whole, but came from a younger stellar environment with less exposure. This visitor's ancient age and extreme velocity pose unknown variables. Should fragmentation occur, debris could scatter in all directions. While most fragments would speed away on hyperbolic paths, leaving the solar system, some could slow enough to become temporary prisoners of solar gravity, creating lasting hazards. Mass distribution could vary widely. One large chunk might retain most of the mass, or it could shatter into dozens of equal-sized pieces, multiplying risks. Even if it survives intact, the visitor faces another ultimate test. Its path intersects directly with Mars's orbit in early November, setting up a potential collision with disastrous consequences for the red planet. Mars orbits the Sun at about 1.5 astronomical units, traveling on an elliptical track that brings it closer and farther throughout its 687-day year. The visitor's trajectory places it in Mars's zone at around the same time the planet might pass through, creating a perilous cosmic crossroad. Collision probability remains uncertain due to timing variables, but the window measures only a few days, narrow yet critical. An impact from an object potentially 3.5 miles across, barreling at interstellar speeds, would unleash energy equivalent to billions of nuclear warheads. Such a collision would gouge enormous craters, hundreds of kilometers wide, blasting vast quantities of Martian soil and rock into space. The impact's heat would instantly vaporize any ice near the strike site, generating a thick temporary atmosphere potentially visible from Earth. Seismic shockwaves could ripple across Mars, triggering planet-spanning quakes and destabilizing ice caps at the poles. Mars's tiny moons, Phobos and Deimos, orbit nearby. Debris flying at escape velocities might collide with them, risking fragmentation or orbit disruption. This scenario complicates current Mars exploration efforts. Multiple rovers, orbiters, and atmospheric monitoring devices operate on and around the planet. A major impact would destroy these assets, setting back robotic and scientific missions by decades. Even a near miss carries risks. The comet's gravity and volatile outgassing could disturb Mars's tenuous atmosphere and slightly alter its orbit. The trail of toxic gases emitted might contaminate the Martian environment for years, jeopardizing future human exploration and colonization plans. As the visitor races onward, crossing paths with Mars adds another layer of unpredictable danger to an already extraordinary cosmic event, the oldest known interstellar traveler moving fast enough to challenge existing science, while posing threats both chemical and physical across the solar system. Mars's thin atmosphere offers little defense against impacts at extreme speeds. Unlike Earth, where most incoming space rocks burn up due to atmospheric friction, Mars would absorb the full force of a collision with minimal protection. Models predict that an impact from this visitor would produce a bright explosion visible from Earth, lasting several minutes. The resulting debris plume could tower thousands of kilometers above the Martian surface, potentially forming a temporary ring around the planet. Ground-based telescopes and orbiting spacecraft would have an unprecedented opportunity to witness such a collision, provided they survive the initial blast. The scientific insights gained would be invaluable, yet the price could be devastating for Mars's current infrastructure. The planet hosts several robotic explorers, orbiters, and instruments collecting crucial data. A significant impact risks destroying these assets and halting decades of exploration. The gravitational interplay between Mars and the visitor might also alter the comet's path slightly, sending fragments on new courses potentially targeting other objects within the inner solar system. Even tiny shifts in trajectory at these scales can lead to enormous consequences over vast distances. Interestingly, the timing aligns with Mars's northern hemisphere winter, when the planet is near its farthest point from the Sun. This seasonal factor could influence how ejected debris disperses and how persistent any atmospheric effects might become, potentially affecting global Martian climate for extended periods. Mars Express from the European Space Agency, alongside NASA's fleet of Mars missions, would need to enact emergency plans if impact risk escalates. This could include shifting spacecraft into safer orbits or temporarily suspending operations to avoid damage from collision debris. Yet, the potential Mars collision is only one possible explosive event on the horizon. Within this ancient visitor lie volatile compounds trapped under pressure for billions of years, now awakening as solar warmth intensifies. These materials could trigger explosive releases rivaling nuclear explosions. Cometary outbursts stand among the most violent solar system events. When pockets of frozen gases deep inside vaporize suddenly, brightness surges by thousands of times in hours. The force can blow away surface layers, exposing fresh ice to sunlight and spurring cascading blasts. This interstellar traveler holds outburst potential unseen before. Cosmic rays over billions of years have synthesized exotic chemicals and crystal structures unknown elsewhere. Subjected to immense pressure and cold, these substances remain highly unstable. Chemical analysis highlights worrying amounts of carbon dioxide, carbon monoxide, and carbonyl sulfide, compounds that exist in solid form only under extreme cold but expand violently when heated. Concentrations here vastly exceed what's seen in normal comets, storing massive energy reserves. Each frozen molecule represents potential energy ready to erupt. After billions of years' accumulation, total stored power could match major volcanic eruptions or large meteor impacts. Surface brightness irregularities already hint at small active vents releasing gas. As solar heating rises, these minor emissions could trigger chain reactions, violently reshaping the object's form and altering its course. Metallic gases such as atomic nickel also add risk. Their presence implies internal heating beyond solar input, capable of sparking outbursts spontaneously. Such explosive events follow erratic patterns, periods of calm abruptly shattered by sudden brightening up to 10,000 times normal levels. These bursts often result from subsurface collapses, exposing fresh ice simultaneously. Objects on their first close approach to the Sun exhibit the wildest outburst behavior. The thermal shock faced by this visitor dwarfs that experienced by native comets, transitioning from billions of years near absolute zero to searing solar heat in days. The rapid temperature swing can cause powerful expansions, tearing the nucleus internally. Debris ejected during outbursts would travel at hyperbolic speeds, matching the parent body's velocity, creating high-speed projectiles crossing millions of miles unpredictably. Unlike typical comet fragments, these pieces scatter on paths impossible to precisely forecast. Multiple bursts could fill space with dangerous debris fields, threatening any spacecraft or planet intersecting their route. Beyond physical collisions, the visitor's toxic gas cloud compounds dangers. Explosive releases would disperse concentrated poisonous plumes lasting years, contaminating regions unpredictably. Predictions for timing remain impossible. Outbursts could start anytime approaching the Sun, happen repeatedly near perihelion, or not ignite until the outbound journey. Adding to the peril, the visitor will disappear from Earth's view as it passes behind the Sun during its closest solar approach. This solar conjunction spells disaster for observation efforts. When aligned precisely behind the sun, ground, and most space telescopes lose all ability to track or monitor. This blackout could stretch weeks or longer, stripping astronomers of any chance to detect shifts in position, behavior, or fragmentation occurring at the very moment danger peaks. The fact that perihelion marks the height of thermal stress, outgassing, and breakup risk means everything could spiral out of control unseen. The duration of this blind spot depends on the object's brightness, solar interference, and telescope limitations. For researchers, this worst-case scenario is every astronomer's nightmare, an enigmatic and potentially catastrophic visitor reaching peak danger precisely when we are blind to its actions. Current forecasts indicate a blackout period lasting between 2 and 6 weeks during which this visitor will vanish completely from our observational reach. During this critical window, catastrophic events could unfold unseen. The object might fragment abruptly, unleash powerful outbursts, alter its trajectory unpredictably, or even disintegrate entirely. The visitor re-emerging from behind the sun in December could be drastically altered compared to the one we last observed in October. Space telescopes positioned at various orbits might offer glimpses during this time, but none can maintain uninterrupted surveillance throughout the solar conjunction. Even instruments like the James Webb Space Telescope and Hubble face a fundamental limitation. They cannot safely point too close to the sun without risking permanent damage. NASA scientists have considered repurposing existing spacecraft to monitor the visitor from alternative vantage points, but current missions lack the right orbital alignments and hardware capabilities to do so effectively. The Parker Solar Probe, which ventures closest to the Sun, was not engineered for comet study and would encounter its own operational challenges if tasked with observing this visitor. Europe's Solar Orbiter mission provides some promise for partial viewing during the conjunction, but focuses primarily on solar physics, not cometary behavior. Re-engineering these assets for continuous monitoring would require significant modifications and resources. Ground-based radio telescopes could maintain some tracking during early and late phases of conjunction, yet radio data offers limited detail on physical changes or fragmentation. Core visual and infrared observations become impossible during the blackout, exacerbating the challenge. Once the visitor returns to Earth's view in early December, astronomers will face another hurdle: reacquiring it quickly. If notable changes occurred while hidden, reacquisition might prove highly difficult or even impossible. Adding to this, winter weather across both hemispheres frequently disrupts ground-based telescopes, potentially extending the effective observational blackout beyond the solar conjunction. While amateur astronomers and citizen science networks may contribute valuable early detections, their instruments lack the sensitivity for detailed chemical or trajectory analysis. Rapid resumption of professional monitoring will be essential to mitigate the post-blackout risks. This blackout period starkly reveals humanity's fundamental vulnerability in monitoring cosmic threats. Despite advanced global telescope arrays and sophisticated space missions, we remain blind to crucial developments during these critical intervals when danger could evolve dramatically and rapidly. To minimize risk, international collaboration among observatories worldwide becomes vital to close observation gaps and maximize data collection once the visitor resurfaces. Beyond observational challenges, the visitor itself raises startling theoretical questions. Some scientists, including Harvard astrophysicist Abraham Loeb and colleagues, propose that this object is not a natural phenomenon, but instead alien technology silently observing our solar system. This hypothesis stems from several anomalies that collectively defy natural explanations: its unprecedented speed, unusual chemical makeup, the forward-pointing particle tail, and its sharp hyperbolic trajectory. While individual oddities could have natural causes, their combination suggests intentional design. The unusual forward-streaming tail, unlike any comet previously known, aligns exactly with what would be expected if the object were equipped with advanced obstacle detection systems, spraying large particles ahead as a protective buffer during high-velocity interstellar travel. Its carbon dioxide-rich atmosphere, far surpassing typical comet compositions, hints at industrial processes rather than cosmic formation. Advanced extraterrestrial civilizations might employ carbon dioxide-based propulsion or cooling systems optimized for deep space. The visitor's remarkable preservation after 7 billion years despite constant cosmic bombardment, also indicates extraordinary durability beyond what natural bodies typically exhibit. Loeb's team calculates that maintaining the large particle emissions seen requires energy outputs far beyond what natural outgassing can provide, implying active onboard power sources. The timing invites deeper speculation. The object entered our solar system during humanity's first century, emitting radio signals and conducting space exploration, our technological fingerprints theoretically detectable across interstellar distances. The visitor's hyperbolic path could reflect deliberate navigation to conduct detailed surveillance across multiple star systems while avoiding capture by stellar gravity. Stealth appears integral to its design. Unlike previous visitors with overt artificial signatures, this object's natural appearance masks its technological essence, evading immediate identification. The absence of electromagnetic signals suggests advanced stealth measures, minimizing detection chances by radio telescopes, consistent with theories that civilizations wishing to survive avoid broadcasting their presence. Its approach from the galactic thick disk, a remote, ancient stellar population, might be a calculated choice, hiding the probe among natural phenomena while gaining optimal observation angles of our solar architecture and habitability. Size and mass estimates fit hypothetical interstellar probes, capable of carrying sophisticated sensors and communication arrays across stellar distances. If this theory is correct, the implications reach beyond mere science. An alien reconnaissance device silently monitoring us calls into question their intentions. Are we viewed as threats or potential allies? The dark forest hypothesis from science fiction imagines civilizations hiding to avoid exposing themselves to aggressive neighbors. In such a universe, stealth surveillance missions assess emerging species before deciding on contact or eradication. Current international protocols for extraterrestrial contact focus on radio transmissions, not sudden physical arrivals of alien artifacts. The discovery of genuine alien technology within our solar system would demand unprecedented cooperation among space agencies, governments, and researchers worldwide. Finally, if this visitor represents a stealth probe, it might indicate hostile civilizations watching us from the shadows. The dark forest paradigm suggests any civilization revealing its location risks destruction by more advanced hostile species. Survival hinges on invisibility, with proactive surveillance and elimination of new entrants. This visitor's sophisticated disguise as a comet, while exhibiting unmistakable technological traits, perfectly fits this scenario. Its stealth technology and timed arrival coincide eerily with humanity's awakening as a spacefaring civilization, whose radio signals have traversed the cosmos for over a century, potentially alerting distant observers. The visitor's unusual chemical makeup might also reflect engineered materials designed for long-term functionality in deep space, with carbon dioxide-based systems optimized for the hostile conditions of interstellar travel. The forward-pointing particle stream likely serves two crucial functions: detecting obstacles for safe navigation and actively scanning target star systems. This technology would enable the probe to conduct thorough surveys while appearing as a natural comet, maintaining stealth without compromising its mission. Its trajectory offers perfect vantage points to assess our solar system's planets, resource distribution, and signs of technological activity. By following a high-speed, nearly straight path, such reconnaissance probes maximize data gathering, while minimizing their exposure to detection or interception by the monitored civilization. The hyperbolic velocity ensures a swift exit after completing observations, lowering the chance of contact. It's possible multiple such probes operate concurrently, approaching from various directions to cover the galaxy comprehensively and provide redundancy in case of losses or detection. The absence of any communication attempts during the flyby aligns with the dark forest strategy, where advanced civilizations avoid revealing themselves to prevent attracting hostile attention. The visitor's astounding age, 7 billion years, indicates that civilizations in the galactic thick disk region may have adhered to such survival protocols for eons, suggesting predatory behavior among advanced species is a stable long-term strategy. If humanity is viewed as a potential threat, this mission might be a reconnaissance precursor to more aggressive actions. Civilizations with the prowess to construct interstellar probes would possess weaponry beyond anything humans could defend against. Our current satellites, space stations, and planetary defense systems would be highly vulnerable, potentially neutralized before we even became aware of an assault. No international or interagency protocols currently exist to respond to hostile alien surveillance or attacks. Facing extraterrestrial threats exceeding terrestrial defense scenarios would demand unprecedented coordination between military, civilian space organizations, and governments worldwide. Beyond theoretical speculation, observations reveal physical features incompatible with natural objects. The stream of large particles ahead of the visitor forms a protective shield resembling collision avoidance systems engineered by aerospace specialists. Extending thousands of miles forward, this particle buffer zone allows detection of obstacles several minutes before impact, offering precious time for course corrections traveling at enormous speeds. Natural comets eject mostly microscopic dust and gases, carried backward by solar winds. Here, however, the emitted particles are large enough to resist solar pressure, while small enough to travel ahead at high velocity. Engineering analyses suggest optimal particle sizes between 1 and 10 micrometers, precisely the range detected. The continuous generation of this buffer zone demands energy input far exceeding what passive outgassing can explain. Maintaining it requires onboard power sources operating constantly throughout the journey, not just solar heating. Moreover, the particle distribution follows geometric patterns rather than random dispersion, forming symmetrically fanned streams ahead of the visitor's course. This structured emission maximizes coverage while conserving energy. Computer models of interstellar navigation show such buffer zones are the most efficient obstacle avoidance method, outperforming electromagnetic or gravitational systems that would need vast power unavailable for long-duration missions. Notably, the particle emissions intensified exactly upon entering the asteroid belt, the most debris-dense section of our solar system with trillions of large rocks, indicating automated activation of these protective measures. The buffer zone's diameter spans approximately 12,000 kilometers, similar in size to Earth's diameter, offering ample detection range for projectiles capable of ending the mission during high-speed transit. Despite increasing solar radiation pressure, the stream maintains directionality and density. Natural emissions disperse randomly under such conditions, but this visitor controls its forward particle emissions with precision. Absence of significant particle outflow in other directions supports a technological rather than natural origin. Material analysis identifies these particles primarily as carbon compounds, with traces of metals engineered for functional properties, distinctly different from natural comet dust or rock mixtures. Velocity measurements of the particles show they slightly exceed the visitor's speed, signifying active acceleration rather than passive release. Sustaining such acceleration requires continuous onboard energy generation, reinforcing the artificial propulsion hypothesis. Remarkably, radar observations reveal structured reflections from the particle stream, matching simulations of artificially maintained navigation shields and confirming geometric organization inconsistent with random natural processes. Automated systems seem programmed to activate buffer zones precisely upon entering densely populated stellar regions, safeguarding the craft from environmental hazards. This represents technological sophistication far beyond humanity's present reach, evidence of civilizations capable of routine interstellar travel and exploration. Further supporting this interpretation is the visitor's electromagnetic silence. Despite high activity levels, visible coma, particle emissions, and spectroscopic signals, it emits no detectable radio or other electromagnetic waves common in natural comets. Typically, active comets generate radio signals from ionized gases, electrical discharges, and heated surfaces. The visitor, however, remains silent across all frequencies, indicating advanced electromagnetic stealth designed to evade detection. Given the importance astronomy places on radio observations to study cometary properties, this absence is striking. Advanced civilizations deploying reconnaissance probes would prioritize stealth capabilities to avoid exposing their presence, making such silence a logical design feature. This visitor's complete silence across radio frequencies is perplexing, especially since its chemical makeup should produce ionized gases naturally emitting radio waves. Yet, Sensitive radio telescopes worldwide detect no signals beyond background noise, indicating more than just passive invisibility. It suggests active electromagnetic suppression technology. Stealth spacecraft are often designed using special materials and shapes that absorb or redirect electromagnetic waves, preventing reflection back toward observers. The visitor's surface appears finely tuned for managing electromagnetic energy, minimizing detectable heat emissions typical of solar-heated bodies. Unlike natural objects radiating energy broadly, it seems equipped with advanced heat control systems that prevent revealing itself through thermal radiation. Even military radar systems, which track stealth aircraft, fail to return clear signals from this large body emitting metallic particles. This points to technology explicitly engineered to thwart electromagnetic sensors. Its hyperbolic course offers an ideal trajectory for silently monitoring our solar system's radio signals and technological emissions, while keeping its own presence hidden. Global radio telescopes have monitored it extensively across multiple frequencies, searching exhaustively for any artificial electromagnetic footprints. The total absence of detectable emissions defies statistical odds for a natural object of this size and activity. Compared to prior interstellar visitors which emitted detectable radio waves consistent with typical cometary processes, this visitor's silence stands out as highly unusual. Advanced signal processing methods, designed to catch faint deep space transmissions, have found nothing associated with the visitor's position and path, despite confirmed outgassing and particle production. Arriving from the galactic thick disk, a stellar population region rich in ancient stars, it occupies an optimal spot for long-range surveillance targeting our communication networks and industrial development. International astronomy facilities have coordinated special campaigns to detect any artificial radio sources aboard it. The inability to detect any emissions strongly implies deliberate countermeasures against electromagnetic detection. This complete silence spans radio waves, infrared, and visible light, suggesting highly comprehensive stealth technology rather than selective frequency blocking. Achieving such sophisticated electromagnetic control demands advanced materials, science, and power systems far beyond current human achievements. The combination of electromagnetic silence with active particle generation and chemical emissions signifies a level of technological complexity impossible through natural processes alone. Its stealth raises profound questions about origin and environment. Emerging from the galactic thick disk, links it to the galaxy's oldest stars formed over 10 billion years ago, when the Milky Way was young and much more chaotic. These stars condensed from primeval gas clouds enriched by the universe's first massive stars ending in supernovae, scattering heavy elements across a turbulent early cosmos. Tracing the visitor's trajectory backward leads directly to this ancient stellar neighborhood. The path aligns with regions dominated by thick disk stars, whose distinct chemical signatures and ages vastly predate our Sun. These stars formed under conditions absent from the modern universe: different heavy element ratios, altered gravitational forces, and dynamic cosmic mergers that dispersed star systems widely. The visitor's atmospheric makeup matches predictions for materials forged in such ancient crucibles, including unusual ratios of carbon dioxide, metallic vapors, and rare compounds formed within the nuclear furnaces of early massive stars. Objects from this region act as time capsules from cosmic infancy, preserving matter and physical processes from the first billion years after the Big Bang. Its formation date near 7 billion years ago coincides with thick disk stars' most intense era of star formation, when numerous supernova explosions enriched the galactic environment with heavy elements at rates never again matched. The visitor's survival as solid matter implies it formed where conditions allowed exotic stable ice formation, a scenario that modern astrophysics finds challenging to replicate precisely. Thick disk stars follow elongated orbits far above and below the galactic plane, increasing the likelihood of planetary system disruption and ejection of bodies into interstellar space. Early galaxy gravitational dynamics, shaped by massive dark matter concentrations and ongoing mergers, created chaotic environments capable of flinging trillions of objects away from their parent systems at high velocities. Current galactic evolution simulations support the existence of vast populations of such interstellar wanderers produced in the galaxy's violent youth, traveling for billions of years. This visitor presents our first chance to directly analyze materials from that primordial era. Unlike distant galaxies where we observe only surface light, this object carries tangible physical samples processed by the universe's earliest stellar generations. Its thick disk origin explains both its exotic chemical composition and extraordinary robustness. Bodies born amid these extremes naturally evolve properties, allowing them to survive cosmic time spans under conditions no modern comet ever encounters. The trajectory indicates roughly 7 billion years of interstellar travel since ejection from the thick disk area, potentially making it the oldest surviving intact object ever sighted within our solar system. The visitor's origin in the galactic thick disk carries implications far beyond scientific intrigue. This ancient stellar region could host civilizations that have had billions of years more than humanity to develop ultra-advanced technologies and spread throughout the galaxy. If the visitor is technology from such a civilization, its creators would have developed capabilities that dwarf all recorded human achievements, potentially achieving interstellar travel long before our solar system even formed. But this distant birthplace raises a darker question. What other ancient visitors might be headed our way from this cosmic graveyard? As the object travels, it continuously sheds thousands of particles, creating a persistent hazard that may last centuries after it departs. Its outgassing releases not only toxic gases but also solid fragments ranging from microscopic dust to sizable chunks of ice and rock several feet across. Traveling at an extreme speed of 61 kilometers per second, these fragments become lethal projectiles, each following its own path through the solar system. Unlike debris from local comets, which settle into predictable orbits, these particles maintain interstellar velocities, spreading widely. Simulations predict this expanding debris field will continue to grow for decades. Individual pieces follow trajectories influenced by size, composition, and release timing. The largest fragments pose the greatest threats. Meter-sized ice chunks could utterly destroy any spacecraft unfortunate enough to collide with them. These fragments, moving too fast for solar gravity to capture, spread into a cone-shaped zone millions of miles long behind the visitor. This vast debris cloud intersects numerous spacecraft paths, satellite orbits, and planetary approach corridors, presently utilized or planned for future missions. Tracking such a vast array of small, fast-moving debris presents staggering technical challenges. Most fragments are too small for current telescopes to detect individually, yet large and dense enough to cause catastrophic damage. The debris field's exotic chemical makeup compounds hazards further. Particles carry the visitor's unusual toxic mix, threatening contamination of surfaces they strike on asteroids, moons, or spacecraft. Fragment speeds vary depending on outgassing dynamics. Particles released during intense activity phases move significantly faster than the parent object, while those from quieter periods lag behind slightly. While debris concentrates along the visitor's trajectory, the particle cloud may spread hundreds of thousands of miles sideways due to momentum imparted during a mission, creating a hazard zone far exceeding the visitor's immediate vicinity. Solar radiation pressure affects particles differently by size. Small dust is pushed farther off course over time, whereas large fragments remain closer to the original path. Current space traffic management systems designed for Earth orbit debris traveling at far lower speeds and predictable orbits cannot track or mitigate risks from interstellar velocity fragments. This expanding debris field threatens missions to Mars, the asteroid belt, and outer solar system destinations. Spacecraft may need to alter timing or flight paths to avoid dangerous regions, potentially delaying exploration by months or years. Some fragments could even gain sufficient velocity to escape our solar system entirely, dispersing exotic materials into interstellar space and contaminating future interstellar travelers. The visitor's lasting influence will far outlive its passage, creating persistent hazards that complicate planetary defense and space exploration for generations. The greatest immediate danger falls on active spacecraft. Unable to evade this invisible gauntlet, valuable billion-dollar missions operating throughout the solar system face risks of destruction from high-velocity impacts. NASA's Parker Solar Probe, studying the Sun's corona, follows an orbit that could intersect the debris field during close solar passes. Its heat shields protect against solar radiation, but not impacts from hypervelocity ice and rock. Europe's solar orbiter undertaking similar observations also encounters increased risks, with debris potentially crossing its path at speeds too great for its shielding. Mars-bound missions are especially vulnerable, as the visitor's trajectory passes directly through Mars's orbital zone, concentrating debris density along common routes. The Mars Sample Return mission, years in development, risks loss before achieving its objectives. Similarly, the Europa Clipper spacecraft, aiming to explore Jupiter's icy moon, launches amid peak debris hazard windows. Delicate instruments and solar panels might not survive collisions with particles traveling 60,000 miles per hour. Even the James Webb Space Telescope, stationed at the Earth-Sun Elyseid 2-point, faces severe risk. A single marble-sized fragment striking its sensitive mirror or instruments could cripple this $10 billion observatory, jeopardizing decades of scientific work. Current spacecraft shielding methods are effective against typical orbital debris moving at a few miles per second, but the visitor's fragments travel at velocities 30 times faster, releasing kinetic energy that overwhelms existing defense systems. The debris' invisibility and unpredictability render avoidance planning nearly impossible. Unlike trackable asteroids or meteor streams, millions of small particles too tiny to detect yet deadly in effect saturate vast volumes of space. No existing international protocols address debris traveling at such extreme hyperbolic speeds. Emergency responses designed for Earth orbit assume known velocities and trajectories, not scattered high-speed fragments across millions of miles. This timing exacerbates risks for burgeoning commercial space activities. Private enterprises investing billions in satellite networks, space stations, and lunar operations face potential destruction from these untraceable hazards. Insurers lack models to quantify risks from interstellar debris contamination, complicating coverage and financial planning. Robotic missions throughout the solar system cannot currently detect incoming debris at sufficient ranges or adjust flight paths fast enough to prevent catastrophic collisions. Most spacecraft operate on fixed trajectories programmed well in advance, limiting rapid evasion options. The hazard extends beyond government and commercial assets, impacting amateur radio satellites, university research projects, and international partnerships focused on space science. As access to space democratizes, hundreds of vulnerable targets without advanced shielding multiply, increasing potential losses. Ground-based monitoring networks track orbital debris, but cannot cope with objects traveling at interstellar velocities on unpredictable paths stretching current technology beyond its limits. Some spacecraft may survive initial impacts, but suffer gradual degradation, microscopic damage to solar arrays, communication antenna disruptions, or navigation system interference can shorten missions prematurely. The cascading losses from multiple such incidents could devastate space exploration efforts, setting back progress by decades and constraining humanity's reach beyond Earth. Scientific missions representing years of work and billions of dollars in investment face the risk of destruction from these invisible high-speed fragments. But even if spacecraft survive the expanding debris field, a more pressing challenge looms: the shrinking window to study this ancient visitor before it vanishes forever. Humanity has less than 3 months to extract invaluable data before the object leaves our reach permanently. This visitor's hyperbolic orbit makes the opportunity truly once in a lifetime. Unlike familiar periodic comets that return every few years or decades, this one will never revisit our solar system. Every day lost in observation means irreplaceable information about the early universe slips away. Global weather has already interfered with critical observation periods. Cloud cover has blocked key spectroscopic measurements during peaks of activity, while atmospheric turbulence has blurred images needed for precise data. Technical difficulties similarly have hampered campaigns. The Hubble Space Telescope struggled with pointing glitches during scheduled observation windows, and Earth-based observatories encountered equipment failures, just as the visitor exhibited unusual behavior. Scheduling conflicts amplify the problem. This rapidly moving visitor's unpredictable activity is at odds with observatory timetables set months in advance. Some facilities prioritize trajectory tracking, others study chemical composition, These fragmented priorities lead to gaps in holistic data collection. The upcoming solar conjunction represents the largest impending observational blackout. For weeks near the visitor's closest solar approach, no Earth-based instruments will track its behavior when thermal stresses could trigger the most dramatic changes. Space telescopes have their own constraints. The James Webb Space Telescope can observe the visitor only during specific orbital periods, while Hubble's aging systems require careful planning to optimize limited observation time. Amateur astronomers and citizen scientists may help supplement data, but coordinating these efforts with professional programs during emergencies is difficult and understaffed. Furthermore, the visitor's brightness fluctuates unpredictably, sometimes growing too faint for detailed spectral analysis, despite favorable positioning, wasting precious telescope time that might otherwise serve other research goals. Data processing delays compound challenges. Raw captures from major instruments need weeks or months for thorough analysis. Vital discoveries may only surface after prime follow-up windows have closed. Budget limitations restrict how many observatories can dedicate sustained resources to tracking the visitor. Many juggle these demands alongside pre-planned projects, forcing tough decisions about scientific priorities. As it speeds past Mars and Jupiter, each planetary encounter offers a rare chance to study gravitational influences and compositional evolution, moments that will never recur. Earth's seasonal weather impacts observational quality too. Northern Hemisphere winter reduces telescope effectiveness at the crucial December period when the visitor re-emerges after solar conjunction. Scientists have been forced to prioritize specific measurements between mapping trajectory, analyzing chemicals, or imaging structure, which inevitably leaves some fundamental mysteries unsolved. Space agencies discuss emergency plans to enhance observation capabilities, but deploying new instruments or repositioning spacecraft requires years of preparation, a time frame incompatible with this fast-moving visitor. Even with perfect observation, the visitor itself defies predictability. Its material loss rate has accelerated beyond all theoretical expectations, risking destabilizing trajectory changes that could send hazardous fragments toward populated regions. Unlike normal comets, which lose mass gradually as solar heat sublimates surface ices, this visitor's outgassing far exceeds typical levels, potentially shedding several tons of material every second. The accelerating mass loss suggests internally driven processes independent of external heating. As material jets stream away, they impart momentum that could alter the visitor's path relative to planetary bodies. Rather than steady outgassing, the visitor's behavior appears exponentially increasing as it nears the Sun, a sign of internal instabilities, possibly leading to fragmentation or explosive outbursts. Its unusual chemical makeup complicates modeling. Most comet mass loss calculations assume water ice as the dominant volatile, but this visitor's atmosphere is carbon dioxide rich, requiring different thermal physics. Cosmic ray bombardment over billions of years may have created internal structures prone to instability as solar warmth climbs. Subsurface cavities pressurized with volatile gases could collapse suddenly, releasing massive gas explosions much stronger than typical comet activity. This accelerated mass loss forms a positive feedback loop. As surface layers erode, they expose fresh interiors to solar radiation, which heats and triggers even more vigorous outgassing, potentially continuing until total nucleus disintegration. Computer simulations cannot reliably predict how such extreme mass loss changes trajectory. High-velocity emission jets could nudge the visitor toward dangerous gravitational encounters with Mars or other planets. Worryingly, the peak mass loss aligns with solar conjunction. When Earth-based cameras go dark, the visitor could undergo violent changes unseen until it reappears. Fragmentation debris spreads along the visitor's general path, but fans outward in widening patterns. These secondary fragments risk impacting spacecraft or planets months after the main body has passed. The visitor's mass loss rates also vary cyclically, likely driven by rotation bringing different surface regions into solar exposure. This variation renders predictions of the next major outburst impossible. Rapid thermal stress threatens to fracture this ancient visitor's nucleus as intense surface material loss reduces pressure on internal regions compressed over billions of years. This sudden relief could trigger explosive decompression events within the core. The visitor's complex chemical makeup ensures various compounds sublimate at different distances from the Sun, producing a layered cascade of mass loss as it nears perihelion. Terrestrial observations confirm the visitor's brightness is increasing faster than mere proximity to the Sun would suggest, indicating that its mass loss is accelerating beyond the norms expected for cometary activity. The comet's enormous coma, the cloud of gas and dust enveloping it, continues expanding, potentially extending beyond Mars's orbit soon, creating a vast atmospheric envelope. This tremendous material loss is comparable to vaporizing small asteroids entirely. If current trends persist, the visitor could shed a significant portion of its original mass before its closest solar approach, fundamentally altering both its physical structure and trajectory. Yet, the transforming mass loss has generated a phenomenon unparalleled in previous encounters. The expanding atmospheric envelope surrounding this visitor now measures more than 200,000 miles across, greater than the distance between Earth and the Moon, and ranks among the largest gaseous structures ever observed in our solar system. This immense envelope of gas and dust surpasses even Jupiter's diameter and shows signs of accelerated expansion as solar radiation intensifies its activity. Previous comets typically develop comas spanning mere thousands of miles, impressive but manageable. Here, however, the atmospheric growth approaches planetary scale, defying all conventional cometary models. Measurements taken over weeks reveal an exponential growth rate for the coma, driven by internal processes becoming increasingly dynamic under solar warming. The atmosphere's vast size means its influence extends far beyond the immediate nucleus, making encounters with toxic gases and high-velocity particles highly probable for any spacecraft or celestial bodies passing within hundreds of thousands of miles. Remarkably, the coma's composition remains strikingly uniform throughout its immense volume, suggesting highly efficient mixing that evenly distributes materials, an order of complexity far exceeding simple diffusion. The solar wind's interaction with such an enormous atmosphere creates detectable electromagnetic phenomena. Charged solar particles compress the coma on one side, while allowing expansion on the other, producing an asymmetric shape stretching millions of miles. The visitor's rapid motion creates a bow shock as its atmosphere pushes through the solar wind and the interplanetary magnetic field, generating electromagnetic signals observable by sensitive instruments across our solar system. This ongoing coma expansion persists well beyond distances where typical comets activate. Most require much closer solar proximity to develop substantial atmospheres. This visitor maintains vigorous outgassing even while outside Mars's orbit. The mass of the extended coma represents a substantial fraction of the visitor's original nucleus, implying dramatic internal transformation. Spectral analyses reveal chemical variations across the coma, indicating multiple active emission regions on the nucleus. Different surface areas release distinct materials, forming chemical gradients within the expanded atmosphere. The coma's enormous size challenges most current astronomical tools. Telescopes optimized for point-like sources struggle to map structure and chemical diversity in an object appearing larger than the full moon from Earth's vantage point. Within this microenvironment, intricate internal dynamics unfold, including convection currents, chemical reactions, and particle interactions at scales comparable to planetary weather patterns. Solar radiation pressure acts variably on the coma's components, pushing some materials faster than others, and continually reshaping internal structures as the atmosphere evolves. Traveling on a hyperbolic path, this massive envelope influences vast regions of interplanetary space, potentially altering solar wind patterns, magnetic field configurations, and particle densities across the inner solar system. Observations indicate coma expansion rates fluctuate with the visitor's rotation period, implying that different nucleus areas dominate atmospheric growth at different times, each spin. Yet, this phenomenal atmospheric growth is more than a scientific curiosity. It threatens to alter the visitor's reaction to solar heating in unpredictable ways, making future behavior impossible to forecast reliably. The intense solar radiation and powerful outgassing produce thrust forces capable of modifying the visitor's trajectory toward Earth, Mars, or other populated solar system zones, with devastating potential. Typically, spacecraft navigation depends on gravity-governed predictable orbits. This visitor violates that foundational assumption as asymmetric mass loss, acts like an erratic natural rocket engine, pushing it in unpredictable directions depending on which nucleus regions face the Sun. As it spins, the variable solar exposure of different areas causes thrust magnitudes and directions to shift chaotically, preventing accurate trajectory prediction and complicating any planned response. Computer simulations reveal that even slight deviations in this visitor's path could have monumental effects across the solar system. A course change under 1 degree during its current approach might steer it toward Mars's orbit just as the planet arrives in that region, increasing collision chances significantly. Calculating thrust is especially complex due to the visitor's unusual chemical makeup. Carbon dioxide outgassing behaves differently than water vapor, and metallic elements add further unpredictability that current orbital software struggles to handle accurately. The visitor's massive coma, stretching 200,000 miles across, acts like a giant solar sail, catching solar wind pressure and exerting additional forces on its trajectory. These cumulative effects amplify uncertainties, making its future course more volatile. Historical examples show how dangerous unexpected comet behaviors can be. Well-studied comets have shifted paths abruptly, sometimes on collision courses. Alarmingly, potential trajectory modifications could occur during solar conjunction, precisely when Earth-based tracking ceases, meaning any changes may remain undetected until the visitor reappears in December. Such delayed detection could leave no time to recalculate impact risks or prepare defenses. Traveling at 61 kilometers per hour, even minor deflections translate into huge positional differences as it moves through the inner solar system over months, magnifying uncertainties regarding potential targets. Mars is the most vulnerable planet, as the visitor currently passes through its orbital zone. Slight course tweaks could synchronize its arrival with Mars's position, increasing the chances of impact. Earth faces lower but non-negligible risk, with catastrophic implications if struck, given the immense kinetic energy an interstellar object would deliver. Current planetary defenses are designed around solar system origin asteroids and comets, with predictable orbits. Visitors arriving at hyperbolic speeds and exhibiting unpredictable mass loss and thrust render these systems ineffective. Emergency plans remain embryonic, limited by current tracking and interception technologies, unable to handle such velocities and erratic behaviors. Trajectory changes might also produce gravitational interactions, altering orbits of asteroids or destabilizing small moons. Preliminary discussions among space agencies aim to establish protocols for unpredictable visitor conduct, but substantial gaps remain. Gas giants like Jupiter could amplify minor deviations into major orbital course shifts, increasing complexity. Global networks of amateur astronomers and professionals have been alerted to report any positional anomalies immediately, providing early warnings. Given the visitor's erratic behavior, impact scenarios can't be discounted based solely on its current trajectory. Continuous monitoring until solar system exit is vital. When the visitor finally reappears from behind the Sun in December, it may look vastly different from the October object. After enduring weeks of intense, unobserved solar heating, the comet could fragment, explode, brighten, darken, or even vanish entirely. The solar conjunction blackout ends abruptly with the visitor's emergence in Earth's dawn sky, offering astronomers a first glimpse of an object transformed by unseen thermal stress. Perihelion passage exerts the harshest conditions any comet can face. Solar radiation there is over 100 times stronger than what the visitor experienced in its 7-billion-year voyage, possibly triggering unprecedented activity. Relocating the visitor post-conjunction poses challenges. Changes in brightness, trajectory, or structure may confound standard search techniques, which assume predictable behavior. Historically, comets emerging from conjunction appear altered, some fragmented into many pieces, others displaying explosive brightening, and a few disappearing entirely after disintegration during closest solar approaches. The visitor's exotic chemistry, dominated by carbon dioxide and metallic compounds, makes pre-conjunction models unreliable for predicting post-conjunction characteristics. If fragmentation occurred during solar heating, Astronomers might detect dozens or hundreds of fragments with slightly varying trajectories, vastly complicating tracking and risk assessment. Alternatively, previously inactive nucleus regions might activate, causing the visitor to emerge strikingly brighter due to explosive outgassing, exposing fresh ice to sunlight. Conversely, catastrophic nucleus destruction could leave only diffuse debris with no visible main body. Winter weather in the northern hemisphere, coinciding with December reacquisition, may further restrict observation quality. Significant deviations from preconjunction orbital predictions are likely if outgassing produces substantial thrust. Astronomers could find the visitor in unexpected parts of the sky. Global coordination among observatories will be essential to rapidly find and study the transformed visitor. Post-conjunction observations promise to reveal aspects unseen during the gentler approach. Internal structure, compositional heterogeneity, and dynamic physical processes revealed by the stress of solar heating. Emergency plans might be necessary if multiple fragments emerge on divergent paths, requiring rapid updates to spaceflight control systems to avoid collisions with spacecraft or planets. Fortunately, December offers favorable viewing conditions for amateur astronomers and citizen scientists who could provide crucial early detections and preliminary assessments during this critical phase. Cutting-edge instruments like the James Webb Space Telescope and Hubble will require urgent reprogramming to analyze whatever form the visitor takes after emerging from behind the sun. Observation plans arranged months earlier may need total overhaul, depending on how the object's characteristics change post-conjunction. Its reappearance might coincide with other celestial events, solar flares, moonlight interference, planetary alignments, which could further narrow available observation windows. However, before revealing any transformation, the ancient wanderer must survive its toughest challenge yet. Its path leads through the solar system's deadliest region, the asteroid belt, filled with over 1 trillion rocks exceeding 60 feet in diameter. Any collision with one could fragment this 7-billion-year-old relic or divert it toward densely inhabited planetary zones. This asteroid belt, a relic of violent planetary formation 4.5 billion years ago, stretches between Mars and Jupiter, posing an immense hazard to anything traveling through at high speed. Although more than 1 million asteroids larger than half a mile have been catalogued, these represent only the largest bodies. The true number of dangerous fragments likely surpasses 1 trillion pieces. The visitor's hyperbolic velocity, around 61 kilometers per second, makes evasion by gravitational maneuvers impossible. Unlike spacecraft capable of changing course to avoid hazards, the visitor must maintain its predetermined path regardless of obstacles. Collision probability depends on the visitor's cross-sectional size and asteroid density along its route. Though space appears vast, at such extreme speeds it encounters many more potential collisions than slower-moving objects. Its vast coma, stretching over 200,000 miles, increases its effective cross-section. While small asteroid fragments may not directly threaten the solid nucleus, they can disrupt delicate outgassing processes. Relative collision speeds may exceed 100 kilometers per second, releasing enough energy to vaporize both colliding bodies instantly. The visitor's unique nucleus composition might react in unforeseen ways to these high-speed collisions. After billions of years of cosmic processing, exotic crystal lattices or chemical configurations could become explosively unstable when struck by shock waves. A significant impact could scatter fragments across the asteroid belt, sparking cascading collision events lasting decades. While the visitor's forward-streaming particle shield may repel smaller debris, any object larger than a few meters would overwhelm such natural defenses. Ultimately, the relic depends on chance to survive this perilous passage. Gravitational tugs from the belt's most massive asteroids could slightly alter its trajectory, potentially steering it toward more dangerous encounters with planets. Minor course shifts can yield dramatic long-range effects. Irregular gravity from uneven mass distribution within the belt adds further unpredictability, potentially perturbing both visitor and asteroid orbits and raising collision risks months after passage. Current technology cannot detect all, potentially hazardous asteroids in real time, especially smaller ones. The visitor's rapid speed leaves no opportunity to track and avoid incoming threats, relying solely on luck. Timing complicates matters. Its transit through the belt coincides with escalating solar heating and outgassing activity. This period of maximum instability coincides with maximum collision hazards, greatly heightening the chance of catastrophic breakups. History shows comets often fragment or vanish after passing through the asteroid belt, succumbing to combined thermal and impact stresses. If this visitor completes the belt unbroken, it will join an exclusive group of the most resilient objects ever observed, strengthening arguments for either exceptional natural endurance or artificial engineering for interstellar journeys. Yet, navigating the belt successfully cannot prevent the inevitable final departure. This ancient messenger races toward ultimate exit, carrying untold secrets back beyond human grasp. Following a fleeting visit, it will accelerate into interstellar space, bearing knowledge humanity might never recover. Its hyperbolic trajectory guarantees a singular event in history. Unlike returning periodic comets, this traveler's visit will not repeat. As it speeds away, simulations predict it will exceed 70 kilometers per second upon re-emerging from solar conjunction in December, swiftly crossing Jupiter's orbit and departing our solar system by late 2026. This final phase has massive scientific significance. Questions about the visitor's makeup, structure, origin, and purpose will remain permanently unanswered once it moves beyond observational reach. No present or planned spacecraft can intercept an object moving this fast. Even immediate mission approval and funding could not overcome propulsion limitations necessary to match its course for in-depth study. Thus, the data already gathered represents humanity's only direct sample from the galactic thick disk region, potentially the universe's oldest matter analyzed firsthand. Decades of future research will mine spectral and observational archives for breakthroughs. This departure marks the conclusion of the most comprehensive collaborative astronomical campaign ever undertaken. Global cooperation among observatories has laid a foundation benefiting future space science endeavors. Final monitoring will focus on the visitor's long-term behavior as solar distance increases. Observing how ancient ices respond to cooling may uncover fundamental cosmic preservation mechanisms. Radio telescopes will strive to detect any lingering electromagnetic traces hinting at artificial processes or novel physical phenomena within the nucleus. The visitor's path points toward the constellation Lynx, near the Milky Way's outer spiral arms, with computer models estimating about 40,000 years to reach the nearest star at current speed. Amateur astronomers globally intend to track the visitor's retreat, as long as instrumentation permits, potentially extending observations beyond professional capabilities through decentralized citizen science. These concluding months hold the key to understanding the visitor's true essence. If concealed alien technology exists aboard, the departure phase could reveal operational systems masked during the approach. International space agencies are creating protocols to archive all observation data permanently, enabling future generations to study this extraordinary visitor comprehensively. As it leaves, the visitor will deposit a vast debris trail stretching billions of miles across interplanetary space, a lasting signature of its historic passage. The visitor's passage leaves a trail of debris that may continue presenting scientific investigation opportunities as future spacecraft encounter fragments during their missions across the solar system. While theoretical models suggest similar interstellar wanderers might traverse our neighborhood every few decades, detecting them relies on advanced survey technologies and favorable viewing alignments, circumstances that might not arise for years or even decades. With this object's departure, humanity concludes its first prolonged interaction with material from another star system, closing a historic chapter initiated by its discovery in July 2025. The final phase of acceleration will test the visitor's structural stability, one last time as the sun's gravity either hurls it back into interstellar space or causes its fragmentation, dispersing ancient matter throughout the solar system. Regardless of its ultimate fate, this brief encounter has exposed unsettling truths about our cosmic vulnerability. It reveals that we inhabit a universe where 7 billion-year-old enigmas can suddenly appear, carrying unpredictable and undefendable threats. This ancient visitor demonstrates that our solar system is a part of a vastly larger, more hazardous cosmic arena than previously realized. Objects originating from distant stellar neighbors can penetrate defenses approach planets, and vanish before full comprehension is possible. Existing planetary defense systems designed against local asteroids and comets prove woefully inadequate against interstellar visitors governed by radically different physical and temporal scales. 7 billion years of cosmic evolution have produced materials and phenomena that stretch beyond current theoretical frameworks. The visitors' exotic chemistry, carbon dioxide dominance over water ice, presence of metallic vapors, and unprecedented particle emission behaviors challenges foundational assumptions underlying planetary science. Its passage highlights critical shortcomings in observational infrastructure. Despite possessing the most advanced telescopes in history, humanity remains vulnerable to observation gaps caused by weather, technical failures, and scheduling conflicts during vital discovery phases. International collaboration, while essential, revealed institutional challenges and competing priorities that limited the ability to mount seamless, comprehensive research during this time-sensitive encounter. The alien technology hypothesis, controversial as it is, demands serious reconsideration of our understanding of cosmic intelligence. If advanced civilizations exist and conduct surveillance, humanity's technological emergence unfolds under watchful eyes, possessing capabilities far beyond ours. The dark forest theory suggests that actively signaling our presence risks attracting attention from civilizations viewing expanding species as existential threats, entities that might eliminate emerging competitors rather than foster cooperation. Emerging from the galactic thick disk, this visitor carries materials older than our solar system, reminding us that ancient objects continue shaping cosmic evolution in profound ways beyond current comprehension. The universe operates on timescales dwarfing human civilizations, with ripple effects spanning billions of years. The debris field trailing the visitor will influence solar system navigation for decades, illustrating how transient encounters with interstellar objects generate lasting, possibly hazardous consequences well after their departure. Accelerating mass loss and erratic trajectory shifts reveal that even natural bodies can behave in ways escaping prediction or control. The cosmos harbors forces and mechanisms beyond human understanding and technological mastery. The increasing accessibility of space has multiplied the number of vulnerable targets, exposing hundreds of assets to destruction from objects beyond our current detection and defense capabilities. The brief windows we have to observe and study cosmic events often mean humanity only gets a single opportunity to unlock deep insights about the universe's nature and history. When these chances are lost due to adverse weather, technical malfunctions, or scheduling issues, they may never arise again. As this mysterious visitor departs, it leaves behind far more uncertainty than clarity, a powerful reminder that the cosmos operates according to laws and timescales far beyond human understanding. We remain relatively young and inexperienced explorers within a universe brimming with ancient enigmas, many of which may remain forever beyond our reach. This experience has revealed that Earth doesn't exist in isolation, but belongs to a vast, evolving, and potentially perilous galactic community. Here, travelers billions of years old can suddenly appear, confront our perception of reality, and vanish back into the depths between stars. The universe makes clear we are neither alone nor safe.